Hello and welcome to the fourth video of the D1 chapter algorithms. Have a go at the quick sort question on the screen if you've got time. Sort the list of names, these, into alphabetical order using the quick sort algorithm. If you're going to do something like this, don't write them all out. They will often be given with first letters that are different so that you can write them like I'm going to here. If not, you could do the first and second letter, but try not to waste time writing all the words out. Pivots on the side, to be clear for the examiner. Middle right is D. We're trying to do it into alphabetical order. B is before D, G is not, H is not, E is not, and N is not. So D goes here and is fixed. Everything else still in its left to right order. Then we've got this list and middle right on this list. B and E. B is fixed, so is D. E, comparing each of these, G, H, and N are all after E, so E goes here, and then keeping the order of these three left to right. Middle is H, B, D, E, all in order. G is before H, and N is not. And then we've got G and N as our final pivots. B, D, E, G, H, N, all fixed in place. All of them have been pivots, therefore the sort is complete. In this video, we're going to do 3 bin packing algorithms. The bin packing algorithms are trying to put items into the fewest possible number of bins. Now, they're not actually going to be bins, but that's the term we use for any of the various contexts this will apply to. It's often visualized as a rectangular bin base with a fixed height across all the different bins. So you'll have lots of these fixed height bins here, and then you're going to put items in with that same rectangular base area, but of different heights. So the first one might come up to here. It's going to be awkward to draw. And then the next one might be a lot shorter in terms of height, and then the next one might be quite tall and fill up the bin. But the key point is you're trying to fit them in and they've all got the same base area. Another sort of situation you might get is if you've got lanes where you're trying to park cars. Maybe you've got 3 lanes on a car carrying ship, and the cars are going to come in this direction, and the cars have different lengths, but they're not going to be put more than 1 per lane. So even though they're not strictly the same dimensions, all you care about here is the lengths. Maybe you've got a bit of wasted space at the bottom here. Maybe this is a slightly longer car, another car, and you can't quite fit the third car in there. A lot of wasted space there. Maybe you've got a really small car here. Maybe not very realistic, but you can hopefully see what I mean. So whether it's boxes, or whether it's cars, or whether it's bits of wood being cut into different sizes, it's the same sort of idea. And we can apply these bin packing algorithms to get the best possible solution. There are 3 that you need to remember. This one, first fit. This is basically the same thing as this, but on an ordered list of decreasing size, and then full bin packing. And this, I think, is the first algorithm where there's a little bit of problem solving involved on your part, rather than just following step by step. You should also be aware of the pros and cons of each of these. I'll just briefly state them as we go through. And you might also need to calculate what is called the lower bound for the problem. And this is not always possible to achieve. What the lower bound is, you just add up all of the values that you've got, the things you're trying to put into the bins, and divide it by the bin size, rounding decimals up. And that will tell you the absolute minimum number of bins that you're going to need. Sometimes it's possible to achieve that minimum number, sometimes it's just not possible because of the different sizes of the items you're trying to pack in. So I'll do a couple of examples focused on this first, and then we'll look at the 3 algorithms on the same list of numbers. So 9 boxes of fixed base area have the following heights in meters. They're going to be packed into large containers with the same base area and height 3 meters each. Determine the lower bound for the number of large containers needed. So if I add all of those together, I get a total of 9.1. 9.1 divided by the bin size of 3 is 3 1/30. So even in a perfect packing world, if we can pack these perfectly to fill the bins, we're going to have 3 full bins, and then we're still going to have 1/30 left over, which you can see isn't actually realistic because all of these are bigger than that. But if it were, we still would have that little bit left over. If that needs to go into a container, that means I need 4 containers total. So you always round up. So 4 bins is my lower bound. Now, for the sake of the examples and highlighting the differences between them, I'm going to change one of those numbers so that that's not the case anymore. So if I change that 0.9, I've changed it here into a 0.8, so that the total now is 9, and that gives us 3 bins. So if you could cut these up, then 3 bins would be enough, but you can't cut them up. So best case scenario, we'll get them into 3 bins, but that's not necessarily possible because we can't cut and slice these up to make that happen. It will depend on whether the numbers come together nicely to make 3 bins or not. We'll come back to that towards the end. So the first fit algorithm is simply to take the items in the order given left to right, put the first item in the first bin, put the second item in the first bin if it will fit, if not, put it into the second bin, and so on. You just take each item in turn, put it in the first bin that has enough space for it, starting at bin 1 and going along. Pros and cons: this is a quick algorithm, but it does not usually give the best solution. In fact, sometimes it doesn't even give a very good solution. But let's see how this works. So use the first fit algorithm to pack these 9 boxes into the 3-meter containers. So what I'm going to do is write bin 1 here, and this is how you'll normally see it written in an exam mark scheme. So I take the first one starting at the left of the list, and I've got 3 meters worth of space, so that 0.4 can definitely go in here. Then I take the second number, 1.2, and I ask, do I still have space to put it in bin number 1, or am I going to need a second bin? There's 3 meters, I've got 2.6 meters worth of space left. Yes, that can fit in here. So 1.2 can go in here as well. That gives me a total of 1.6 meters in that first container. So I've got 1.4 meters left. So the 0.9 can also fit in here. But now we have a first problem item because that gives me 0.5 meters left of space in this bin. And some people like to write that on the side as a reminder later. For example, if this last item here was a 0.4, then I'll want to remember to be able to put it in that first bin. So that 1.0 here, which is our next item to pack, that is going to have to go into a second bin. The bin number 2 has got a 1.0, and you might want to keep track of the space left on the side as you go through as well. That's okay. Then my next item, 1.3, and this is the bit a lot of people will forget, and it is annoying if you do have a smaller number later on than this value here. You must remember to compare it to the first bin. So the 1.3, compare it here first. Will it fit in bin 1? No. Okay, then it goes in bin 2. Then I can add that onto my bin 2 total, so that's 2.3, so that's 0.7 left. Next item is a 0.6. Can it go here first? Still no. Okay, can it go here? Yes. 0.6, that takes this one down to a 0.1. Next item, 1.3, can it go here? No. Can it go here? Definitely not. Bin 3 it is. And we knew we were going to need 3 bins, at least. So that's a 1.3, so I've got 1.7 left in this bin here. 0.8, can it go here? No. Here, no. Here, yes. 0.8 in here. Then I've got 0.9 meters left. Final item, 1.5, can it go here? No. Here, no. Can it go here? No. It needs to go in bin number 4. And that gives me 1.5 meters left of space. All of my containers have been packed. I needed 4 bins. So that's the first fit algorithm. You simply go left to right, and each time you get to a new item, you try to put it in the first bin. If it won't fit, go on to the next one. If it won't fit, go on until you find one in which it will fit, making new bins as necessary. But as you can see, there's quite a lot of wasted space there, and we didn't get down to our 3-bin optimal target. Second algorithm is the first fit decreasing algorithm. This is basically the same thing, but first you sort the list into descending order, then you apply the first fit algorithm. Pros: this is still quite quick, and it often gives a better solution if you start with the list in order, but it doesn't always give the best solution. Let's apply it to the same list of numbers and see what we get. So I'm not going to go through a sorting algorithm. The question didn't say I had to, so I'm just going to write them in order. Another 1.3, 1.2, 1.0, 0.9, 0.8, 0.6, and 0.4. Okay, now it's in order. I do the same thing as before, starting with the first item into the first bin with enough space, which is obviously the first bin. 1.5 left. 1.3, will it fit in here? Yes, it will. Okay, in it goes. And that gives me 0.2 left. Bin 2 for the next one, 1.3 here, and then 1.7 of space. Next item is 1.2, obviously won't fit in the first one, but it will fit in the second one, and that gives me 0.5 space. The next item is 1.0, that won't fit in either, onto bin 3, 2 space. 0.9 won't fit in the first two, but it will fit in the third one. That gives me 1.1 left. 0.8 won't fit in the first two, but it will in the third one. 0.3 left. 0.6 won't fit in any of them, onto bin 4. With 2.4 left. And then 0.4, although it won't fit in bin 1, will fit in bin 2. So 0.4 needs to go here. And this is the first fit decreasing algorithm. You can see that I've got a little bit less wasted space, but I did still need 4 bins. It's a slightly better solution, although not in terms of number of bins used. Our third algorithm option is called the full bin packing algorithm. Now there's a bit of problem solving needed here, because by inspection just means you have to look and see for yourself which items will combine to give a full bin. If you can find items that combine to give you a perfectly full bin, pack these first as a single bin, then the items you've got left over, pack them using the first fit algorithm. Pros of this one is that it will usually give you the best solution, but the cons are it takes time and effort, and the more items you have, if you apply this to a real life scenario, if you've got 1,000 containers going onto a ship or something, it becomes ridiculously difficult to do in the way that I'm about to do it. So same thing here, we've got 3 meters worth of space. The question is simple: can I find some items that will add together to make 3 meters exactly? The answer to that is yes, because I've got a 0.4, a 0.6, that gives me a full 1, a 1.2 and a 0.8. That gives me 2. So in total, I can have these 4 items in one bin with no wasted space at all. Now I look at the remaining items. Can I find another full bin? I think no. So now I have to do the first fit algorithm with the remaining 5 items. So bin number 2 has 0.9, and then 1.0 can fit in here. 1.3 cannot, so that goes in bin 3. Then the next 1.3 can't either, that has to go in here as well. And then the 1.5 has to go into a new bin. It doesn't look any better. However, in this case, there are different options. So if I clear that off, now if instead I combine 1.3, 2.6 and a 0.4, then in bin 1 I can get a full bin here, and now I can actually use a 1.2, if I indicate it slightly differently with boxes, 0.8 that's a 2, and then this one here, that will give me bin 2 also full. no wasted space. And I can get these 3 in a bin as well. So if you're careful with this, although it tends to take more effort and more time, you can get a better solution. And in this case, we didn't need any bins more than what we had for the lower bound. This solution is called an optimal solution. And that's simply a solution where the number of bins that you've used is equal to the lower bound of the problem. But to be really clear on this, that is not always possible. Even if you've got the very best solution to the problem, it is not necessarily going to be an optimal solution. You might have to use more bins than the lower bound. The lower bound is not always possible to achieve. Okay, a different sort of context here. A project takes 16 hours to complete. Each activity takes the following number of hours. And I've done this because this is often the way you'll see it written out. In brackets is the value we're using. The letters are just a way of referring to various activities or cars or whatever it is that the context is using. Apply each of the 3 bin packing algorithms to find the number of workers they would require. Okay, let's start with the first fit. Bin 1 is A5, and that'll have 11 left over. And then 9 will fit in there as well, and that will give me 2 left over. So C will have to go into bin 2 with 8, and that will give me 8 left over. Activity D, although it's small, still won't fit into bin 1, so that'll have to go here as well, giving me 5 left over. E can then fit in here as well, with just 1 left over. Bin 3 is necessary for F, with 11 left over. G will fit with 3 left over, and H is going to have to go in its own bin with 11 left over. First fit decreasing, I'll have to order them. B is first, C with 8, and then G with 8 as well. We've got A, F, and H, and then finally E and D. Bin 1 is B with 9, 7 left over. Bin 2, C with 8, 8 left over. G will not fit in bin 1, but it will squeeze in bin 2 for none left over. That's nice, that's a full bin. A will then go into bin 1 with 2 left over. Now we're going to need bin 3, F with 11 left over, and H to take that down to 6. So E will have to go in here as well, down to 2, and then D won't fit in any of those. Bin 4 needed. 3. And although I didn't calculate the lower bound for the problem at the beginning, I can see that the lower bound is 3 bins because I've got 4 units worth of space here and only 3 units in this bin. So in the full bin packing problem, the question becomes, can I arrange it so that 3 of these 4 units are in the same bin and I can squeeze D into that bin without using a 4th bin? So an optimal answer here would use 3 bins. The answer to that is yes. I've got the 8 and the 8, but if I increase that and I decrease that, then these will also add together, give me a full bin. I say it like that just because that's how it sounded in my head when I thought it. So we've got C8, G8, bin 2 I can get full by doing B9, E4, D3, and then bin 3 is left with A5, F5, and H5, and even has 1 spare. So in this case we need 3 workers. Worker number 1 does these 2, worker number 2 does these 3, and worker number 3 does these 3, and will be finished an hour before the other 2, but the whole project will be done in exactly 16 hours. Final example, an exam question. Use the first fit bin packing algorithm to determine how the numbers listed above can be packed into bins of size 5. No context here, we've just got the numbers and it's the first fit bin packing algorithm. So as with all the others, you need to remember these algorithms. In the exam, they will not be given to you. So bin number 1, I've got 2.6 and 2.4 left over. 0.8 can go straight into there with 1.6 left. 2.1 cannot go into there. It needs to go into the next bin with a 2.9 left over. 1.2 can go into the first bin. 0.4 left over. When I say it can go in, what I mean is it must go in. If that's not in that right place, the examiner will not be able to give you all the marks. Next number is a 0.9. That will have to go here. 2 left over. And then 1.7 can go here as well. 0.3 left over. Bin number 3 needed. 2.3 with a 2.7 left over. 0.3 in this first bin with a 0.1 left over. 1.8 will have to go in the third bin with a 0.5 left over. And 2.7 will have to go into bin number 4. That is our finished answer. Hopefully that is enough for you now to have a go at the practice questions in exercise 1E. And maybe I'll see you for the final video in this chapter, binary search.